Take again that X is a stochastic process, which this time has a continuous index set, so I is a subset of R, and the state space is still discrete, so we still have a finite or a countable set of possible outcomes. In this case, X is called a Markov jump process if it satisfies the Markov property. Furthermore, if the conditional distribution again only depends on the distance between the two random variables and not the time point that you are looking at, this stochastic process is called a time homogeneous Markov jump process. Such a time homogeneous Markov jump process is often defined through the Q matrix. The Q matrix, which is built up by the transition rates from xi to xj and the holding rates in xi. Let us define delta ijh as the probability that the state at time point t plus h is equal to xj, given that the state at time point t was equal to xi. So basically it is the probability that after a time lapse h, we have moved from state xi to state xj. If we then divide delta ijh by h, and we let h go to 0, so we take the limit h to 0, this means that the time frame, the time lapse h goes to 0, then we obtain a rate of change, which is called the transition rate, to go from this state xi to the state xj. And then if xi is equal to xj, so basically we do not change, we stay in the same state, then the limit of 1 minus delta ijh over h for h going to 0 is called the holding rate in this state xi. A typical assumption is that all of the transition rates are positive but finite, and that the holding rate is equal to the sum of all the transition rates. In that case, in my matrix Q, every row sum will be equal to 0. For X, a time homogeneous Markov jump process, let us denote the arrival times by capital T. So capital Ti, these are the moments in time, so the time points at which the process, the Markov jump process, will change state. The sojourn time in a certain state is the time that the process spends in this state xi. So, for example, if we go to x1, then the sojourn time of x in state x1 is the amount of time, the minimal amount of time spent in the state x1 before jumping to any other state. It can then be shown that these sojourn times, they are exponentially distributed with a mean sojourn time of 1 divided by qii, so 1 divided by the holding rate. Furthermore, if we look at the stochastic process, the Markov jump process, in specifically the arrival time, so we define a new stochastical process x hat as being the previous Markov jump process but only for the arrival times, then this x hat is a Markov chain, which we call the jump chain, and the transition matrix is defined as being the transition rates divided by the holding rates. This leads to a jump and hold description of the time homogeneous Markov jump process. So after jumping into state xi, the process will remain in this state for a random time which is exponentially distributed, and after this random time in the state xi, it will jump to another state, j, which is different from I, and the probability is given by the probabilities of the matrix P hat. For a given unknown Q matrix, we can calculate the matrix P hat, and then we can use algorithm 4 to generate realizations of a time homogeneous Markov jump process. So recall capital T's are the arrival times, and in the algorithm a capital Y indicates a certain state, and capital A are the sojourn times. Start by setting arrival time 0 to 0 and draw y0 from its distribution. So given the distribution, we draw an initial state y0, and then we say x0 is equal to y0 is equal to the initial state. So n is now equal to 0. Then we draw a first sojourn time a1, which we know is exponentially distributed with parameter q00, q00 being the diagonal element of my Q matrix, which corresponds to the state y0. We then know we stay in this state y0 for a time a1, a sojourn time a1, And so the next arrival time, t1, will be t0 plus my first sojourn time a1. Since we know that we remain in the same state up to t1, for every small t between t0 and strictly smaller than t1, we set xt equal to y0, so to the initial state, and only at the time t1, then we change the state. So once we arrive at the time point t1, the arrival time t1, we will change state to one of the possible states that we can go to. And to determine this new state, we will use the distribution corresponding to the y0th row of p hat. So the row which gives us the probabilities to go from state y0 to any other possible state. And then we repeat this process for all n larger than 0.